Hey there, I'd like to give you a little refresher about circular motion. This is just like a Cliff Notes version so that we can get you current to do these combination problems we've been working on. Important things about circular motion is that the net force always needs to point inwards towards the center. And so whenever something's going in a circle, it needs to have an unbalanced force pointed inward. It also has an acceleration pointed inwards. And that acceleration can be found by doing v squared over r. We can link the net force with the acceleration by saying F net equals ma, or A equals F net over m. This is how it's on your equation sheet. In fact, both of these are on your equation sheet, which is great. And so you can put those two together when something's going in a circle. Common circular motion problems include like a vertical circle. So one vertical circle that we might do would be like a ball on a string. So a ball on a string might be at the top of the circle or at the bottom of the circle. And we would say, well, of course, there's a force of gravity acting on it. It goes straight down. It's the same size at both locations. Gravity is equal to mg. But there's also a force of tension acting on it. And so at the bottom of the circle, because I need a net force pointing at the center of my circle, the force of tension has to be larger than the force of gravity. I would say that my net force at the bottom has to be the tension force, which is bigger, minus the force of gravity in order to have an unbalanced force inward towards the center of the circle. At the top of the circle, the force of gravity is already downward towards the center, and tension in ropes can only pull. So if there is tension, it's also pointed downward. At the top of the circle, we would have something like tension plus the force of gravity working together to be my net force going inward towards the center. The same idea is true for maybe like a ball going through a loop. When you have something again going through a vertical circle, this ball could be at the top of the circle or the bottom, or the places we care about, because that's where our forces can point directly at the center and make life easy for us. So we still have a force of gravity that would be going straight down, the same size at each location. Now it's a normal force that's going to work with us. But again, to have a net force pointed at the center, at the bottom, the normal force has to get large. And that's why you feel heavy, because you feel your normal force. What that means is you experience that as your apparent weight. So if it says how heavy do you feel or what's your apparent weight, they're talking about your normal force, not your force of gravity. Your force of gravity is your actual weight. This is how much you weigh. It doesn't change when you go in a circle, but you feel heavier or lighter because your normal force gets bigger or smaller. At the top of the circle, gravity is already helping you turn, so you don't need as big of a normal force. That helps you to feel a little lighter in your seat when you're at the top. Again, we would say that the net force at the top would be like Fn plus Fg. They're pointing together. We could set that equal to ma, or that's the same thing as like mv squared over r. And at the bottom, we could say something like Fn minus Fg is equal to my net force, or that would be equal to ma, or mv squared over r. If we had something that was going like at an angle, we could have like the Flying Pig Lab or my keys, anything that's like flying around on like this horizontal circular path like that. We could then say, all right, well, it still has the force of gravity going straight down, but that's not pointing towards the center of the circle or away from the center of the circle. So I guess it must get canceled out by something. Here there's a force of tension in the direction of the rope again, not the length of the rope. And when we have forces at angles, we need to remember to break them into components. So that force of tension will have an x component, Ftx, and a y component, Fty. In order to go in a circle, typically we go at a constant speed. If that's true, We're not lifting, we're not lowering. We would say our FTY and our FG are going to balance each other out to keep us going in that constant circle in that horizontal path. And that really it's our FTX that's equal to our net force, or MA or MV squared over R. And sometimes we give you something with like an angle, or we do Pythag. So we could say a couple of things like FTX squared plus FTY squared equals FT squared. Or let's say they give us like the angle the string is at or something. Then we could say something like the tangent of that angle is equal to the opposite of FTX over the adjacent of FTY. And that's powerful for us because we could set the FTX equal to our net force or MA. And we said that FTY was equal to FG or MG. And so all of a sudden we can do some weird stuff and make some magic happen. But it all comes from just understanding like where these connections are made. Maybe the last couple of things we need to talk about back to these is that the velocity is tangent to the curve. So if the string broke at the top, the object might be launched horizontally, like from the top of the path, and go to the ground. If the string broke at the bottom, the object would also be launched horizontally and make this path down to the ground. And so in order to be launched at an angle, the string would have to break at some place other than the top or the bottom. If the string broke like straight over to the side, then it would be launched straight up. If the string broke straight over to the other side, it'd be launched straight down because again, the velocity is tangent to the curve. And so that kind of helps us know if we're launched at an angle horizontally and what velocity to use for like our projectile portion of the problem. Last but not least, we do have some critical speeds. And so when we're talking about critical speeds, we're talking about the minimum speed that a ball could be going at the top and the maximum speed that a ball could be going at the bottom in order to just barely make the loop. The maximum speed happens when you have your maximum net force, which is just the force of gravity. Your minimum speed happens when your minimum net force, which is also just the force of gravity. And we derive these equations by saying, hey, if gravity is my net force, what speed would I need to be going at? Well, I don't see speed here, except net force is equal to MA, and A is equal to V squared over R. So actually, I can set my force of gravity equal to MV squared over R. My force of gravity, that's just mg. So I could set mg equal to mv squared over r. And when I use this equation, v equals the square root of rg, this is only good if gravity is the force pointing at the center of the circle, and it's the only one, right? It has to be that your normal force is equal to 0, there's no other forces, and then we can use this equation for a critical speed. All right, I hope you